Okay, so I'm going to start with where we left off, which was at the beginning of 4.1. And I'm hoping to get through 4.1 and 4.2 today. I have the handouts up there if you guys need one. It's just one of each. So I already kind of went over what a polynomial function was. I defined these terms, the leading term, leading coefficient, and the degree of a polynomial. So we already talked about that. And then I started going over these examples down here of these graphs. And I'm going to kind of go over that again with y'all, just to refresh your memory. So the first one, the first example here, x squared plus 3x plus 1, we all should know that this is a quadratic. The largest exponent is 2, so the degree is 2. The leading coefficient was 1 because that's the number being multiplied in front of the x squared. And the leading term is the entire x squared, the first term. And then the next one, since it's just f of x equal to a number, -3, this is called a constant polynomial. And the degree would be 0 because there is no variable term. So that's the same thing as, this could be written as x -3 times x to the 0 power. Because what is anything to the 0 power? 1. Perfect. So that would just be -3 times 1. And the leading coefficient would just be -3. And the leading term would also be -3. And then the next one we call a cubic because the largest exponent is 3. And that is what the degree is. So the degree is 3. So that's a cubic. The leading coefficient is 2. And the leading term is the entire 2x cubed. Because that's the term with the highest exponent. And then the last one, the degree is 4. And so this is called a quartic. And the leading coefficient is -1. And the leading term is the entire -x to the 4th power. Because that's the term with the largest exponent. Okay. So this note down here says that the graph of a polynomial function is continuous. So this means that there's no holes in my graph. Continuous means I can start with my pencil and trace my graph from left to right, and I'm using the quadratic as an example here. From left to right, and I never have to pick up my pencil. So it's continuous. It's continually going on, and all of these are continuous. The line is continuous, the cubic is continuous, and the quartic is continuous. There's no holes or breaks. It also is smooth. Polynomial functions are all smooth. So remember when we learned about the, I'm going to write examples of non-polynomial functions. I'm going to give you a couple of examples of functions that are not polynomials. So one that we learned about was the absolute value function. Remember that this function had a sharp point. It always looked like a V. Remember that? This would not be a polynomial function because it's not smooth because of that sharp point that makes the V. Smooth means it's curvy, okay? Or a straight line, but no sharp points. And furthermore, the domain of a polynomial function is the set of all real numbers. So that's always true for all polynomial functions. And you can see that in those 4 pictures of those examples, all of the domains of all of those would be all real numbers. They're constantly going from left to right. So the domain is all real numbers. A couple more examples of functions that are not polynomial functions. I kind of mentioned this last time, but anything that has a variable in the denominator of a fraction. This is not a polynomial function. And that function looked like this, if you remember. And I'll draw my axes here. This is a very rough draft. But this was on your library of functions. And it looked something like that for the function 1 over x. This is not a polynomial function. Visually, it's not because there's a break in my graph. There's a complete hole in between, imaginary line in between these 2 parts of the graph. See, the graph, the black parts are not touching that axis. So there's a skip in my graph, so it's not continuous. And also, this x, when it's in the denominator, this is the same thing as x to the negative 1 power. I don't know if we remember that exponent rule, but whenever you have a variable in the denominator, it's known to have a negative exponent. And trying to think of another example. Anything with a radical will also not be a polynomial function. Because what's the exponent of this?
X.
No? Close. How can I rewrite the square root of x with an exponent?
X times X.
No. No.
X squared.
We did talk about this. When we talked about radical properties, this is the square root. Technically, there's a 2 there and a 1 here. So this has a fraction exponent.
X and a half.
1/2.
Yeah.
1/2, exactly. So this is not a polynomial function because the exponent is not a whole number. And that's in the definition at the top. So anything with a radical will not be a polynomial function. Okay, so those are just a couple of examples of non-polynomial functions. Okay. So the first thing we are going to talk about, because we're going to be talking about how to graph polynomial functions, how to analyze their graph, just like we've really been doing with all kinds of graphs so far. So one thing that we can use to analyze the graph of a polynomial function to get some of its properties is by using this leading term test. So it's called the leading term test because we're going to use the leading term in order to determine what's happening at my graph at the endpoints. So where is it going as it goes to negative infinity? What's my graph doing? And what is my graph doing as it's going to positive infinity? So that is called the end behavior of a graph. Okay, so this says if an times x to the n, this is just the leading term as it was defined on the previous page. If that's the leading term of the polynomial function, then the behavior of the graph as x approaches positive infinity. So that's going to mean what's happening to our graph as we get closer to positive infinity. So what's happening in the right direction. Or as x approaches negative infinity, so that will be the left direction of our graph. It can be described in one of the four following ways. So I like to break this little graph up like that. And I'm going to explain what this means. Okay, so if n, and remember, n is the degree of the polynomial, right? It's the highest exponent of our polynomial. So if the highest exponent of our polynomial is even, so if it's 2, 4, 6, 8, whatever, even number, then our end behavior will be going in the same direction. So I kind of, remember that. It's even, okay, it's doing the same thing on both ends. So there's two cases. It's either going to be both going up, like smiling, or both going down at the ends, like frowning. The squiggly lines in between means that other things can be happening in between. We're just talking about the very end behavior of our graph. So it'll be pointing up and smiling if the a sub n, which is the leading coefficient, the number, if that's positive, okay? We learned that about the quadratic. If a was positive, it was pointing up, right? So that is the leading coefficient. If it's positive, and if the exponent is even, like x squared, then it's pointing, they're both pointing up. If it's negative, then they're both pointing down. It's frowning. Okay. The next case is if the exponent, the largest degree, the highest exponent is odd, well, then my end behavior is going off in different directions. It's either going to be the first case here or the second case. So the way I remember this one is if my leading coefficient is positive, then it'll be increasing from left to right. So it starts by pointing down on the left, but then it goes up to the right. So if my leading coefficient, which again is what it's saying up here at the top, if it's positive and the degree is odd, then my end behavior will be going in different directions, but it'll be always increasing from left to right. This is increasing, right? If I put a stick man on here, it's increasing, and then it's increasing here. So if it's positive, it'll be increasing from left to right. And then if the leading coefficient is negative and the degree is odd, then it'll just be going in the opposite way. It's kind of decreasing from left to right. Now, in words, the way that you'll see this described in Pearson, so let's talk about the first blue one. This says, this would be, in words, described as falls to the left and rises to the right. It's one way that they can describe it in words in Pearson. And then this one is described as rises to the left and falls to the right.
So you're saying for the leading test term, we basically looking at the highest exponent and then the leading coefficient
Yep.
to do this?
Yep.
Okay.
Mm-hmm.
Okay.
Yep. And we're going to do a few examples.
It's not always gonna be lined up right in the equation, right?
Correct. Sometimes they can put it out of order. Like you talking about the leading term?
Yeah.
Yeah, sometimes they can put it out of order. You just have to know that the leading term is always the one with the highest exponent. Okay, so the first example, and on Pearson, they can ask you these questions. They can either just have you describe them with words, and they'll give you multiple choice, or they can give you multiple choice of graphs and choose the graph that has the correct end behavior. So it can be either one. And I'm going to kind of do both on these examples. I'm going to draw it for you. So number 1 says, determine the end behavior of the function f of x equals 3x to the 4th power minus 2x cubed plus 3. So here, the leading term is 3x to the 4th. That's my leading term. So that's all I'm looking at to answer this question. Nothing else matters. The leading coefficient is 3, and the degree is 4. It's the highest exponent. So the highest exponent is 4. That's even. So automatically I know that it's going to be my end behavior will be pointing in the same direction, either both up or both down. The leading coefficient is 3. That's positive. So will it be pointing up or down? Up. Perfect. And let me move this a little bit. Okay, so in descriptive form, they'll both be pointing up in the same direction, so it will rise to the left and rise to the right. And then if they give you multiple choice of graphs, you just need to pick the graph, or a lot of times they'll just give it to you like this too, with little squigglies in between. So you'll be doing the very first case. They'll both be pointing up, and whatever's happening in between doesn't really matter. Okay, number 2, same thing. Determine the end behavior of the function. F of x equals negative 5x cubed minus x squared plus 4x plus 2. So my leading term is negative 5x cubed. My leading coefficient -5, and my degree is 3. That's my highest exponent. So my degree is odd. When my degree is odd, I know that they're doing different things. They're either going like this or they're going like that. Going in different directions. And my leading coefficient is negative. So on this one, I'm going to draw the graph first because it's easier for my brain to process what the graph is doing, or it's easier for my brain to write the descriptive form if I draw the graph first. So remember I said, okay, odd going in different directions, negative, it has to be decreasing from left to right. This is negative. So that means it would have to be pointing up to the left and then down to the right in order for it to be decreasing from left to right. So descriptive form, exactly. This one rises to the left and falls to the right. Is making sense so far? Okay. Personally, I think this is easier than a lot of the stuff we've done so far. Okay, number 3. Determine the end behavior of the function x to the 5th power plus x over 4 plus 1. So the largest exponent I see here is 5. So x to the 5th is my leading term. What's my leading coefficient? 1. And then my degree is 5. So my degree is odd. And my leading coefficient is positive. It's the opposite of the one we just did. Because it's odd, so I know they're going in different directions. Has odd behavior. And it's positive, so it needs to be increasing from left to right. And in descriptive form, this would be falls to the left and rises to the right. Looking scary outside. Okay, last one. Same thing. Determine the end behavior of the graph. So this function is f of x equals negative x to the 6th power plus x to the 5th minus 4x cubed. So my leading term, which again is the term with the highest exponent, is negative x to the 6th power. So what is my leading coefficient? -1. Perfect. And my degree, 6, highest exponent. I can't really go up anymore. Do that, I guess. So the degree is even. So when the degree is even, I know that they'll be pointing in the same direction. And the leading coefficient is negative, so they will both be pointing down. So it'll look something like this. And then, you know, whatever's happening in between, again, doesn't matter. I'm just talking about the end of the graphs. So descriptive form, this would be falls to the left and falls to the right. So those are all 4 cases right there. Now, we're going to see, this is the end of 4.1, right? Yeah. So 4. In my opinion, as long as you understand this, the homework for 4.1 and 4.2 is really not that long. Like, I mean, it has quite a bit of problems, I think. I don't know. But it shouldn't take you that long. You're just looking at it and then picking the correct graph. So even when we go to 4.2, which we're about to do, it's all about graphing these polynomials. A lot of them, you can use this rule right here to pick the right graph out of the multiple choice that it gives you.
Did I miss this? The find the zeros?
No, we're about to do that.
Okay, that's 4.2.
Yep.
Oh, okay.
So we're about to do 4.2, and like I said, a lot of 4.2, it's going to ask you to graph a polynomial, and it's going to give you a multiple choice of pictures of graphs. You can do most of them by using this rule and using process of elimination. So this rule is very useful. All right, so let's go on to 4.2. Or, I'm sorry. I'm so sorry. I meant the end of 4.1. 4.1 part 2. I was getting a little mixed up. 4.1 part 2. So we're still in 4.1. Okay. So we've talked a lot about zeros. I've tried to drill that in your head so you understand what that means. Here's another definition. I think I've already given you a definition of a zero, but we're going to talk about it again here. So we're going to be talking about how to find the zeros of a polynomial function, which again, we already know how to do that. We've already done this. Same thing. So nothing really new here. But anyways, so the definition C, some number C, is a real zero of a function, which means that if I plug C into that function, it should be equal to 0, right? It makes the function 0. And if that is true, if C is a 0, then we've also learned that C comma 0 is an x-intercept. We've talked about that many times. And we have learned that in order to find a 0, we do what?
Set the equation equal 0.
Set the equation equal to 0. And then solve for x. So that's how you find a 0, which is an x-intercept. And when you're on the x-intercept, then I'm just doing a random point here. When you're at on the x-axis, what is y equal to? 0. Y is equal to 0 right here. Doesn't even matter what x is. Y is always 0 when you're on the x-axis. So if I wanted to find a 0 of a function, I would set this equal to 0. That's not what we're about to do, but I'm just explaining. I would set this equal to 0 and solve, because I'm plugging in 0 for y. And f of x is y. Okay. Just making sure we understand that. But number 1 is saying to determine whether 2 is a 0 of the function by using substitution. So this is just a question that you'll see in your homework. It'll give you a number, and it wants you to determine whether this is a 0, which means we're going to plug it in for x, which might be what you were getting to, and then see if it equals 0. Make sense? Because if it is a 0, it should make it equal to 0. Okay? So I'm going to plug 2 into this function, which will be 2 cubed minus 2 times 2 squared minus 8 times 2 plus 1. And we're going to evaluate. So 2 cubed is 8. 2 to the second power, which is what I would have to do first because exponents first, is 4. 4 times negative 2 is negative 8. Negative 8 times 2 is negative 16. Bring down my plus 1. 8 minus 8 is 0, so that cancels, but it leaves me with negative 16 plus 1, which is negative 15. So this is not equal to 0, so therefore 2 is not a 0 of the function. So they're kind of just making you go backwards with these problems. They want you to see if this makes it 0, which it didn't, so it's not a 0. Now, if you get a problem like this and they ask you to see if it's a 0, you plug it in and you do get 0, then of course, yes, it will be a 0. Okay, now number 2. This is a different type of problem. This says find the zeros of the function. So what do?
Would you set each one equal 0?
Yes, exactly, but you're skipping a step. First thing I'm going to do is set the whole thing equal to 0, right? Because to find the 0, we need to let y equal 0. And f of x is y. F of x is y. So I'm replacing f of x with 0. Oh, first. But exactly. What you said. Now, this is in what kind of form? What would you call this? What is this? Factored. This is factored already because it's a product of things. So it's already factored for me. So to solve this, I can just set each factor equal to 0. So I would have x minus 2 all cubed equal to 0, x plus 5 equal to 0, and x minus 1 equal to 0. So I have 3 equations now to solve. Bless you. Okay, and don't let this exponent of 3 trip you up, because does anyone remember how I get rid of that? You take the cubed root. That's the inverse of that, which means I also take the cubed root of 0, which will still just be 0. So on the left, that cancels my exponent of 3, leaves me with just x minus 2. And on the right, cubed root of 0 is still 0. So really, all I really need to do is set the inside x minus 2 equal to 0. Make sense? Okay. So now I would add 2 to both sides, so x would be 2, right? X would be negative 5, and x would be positive 1. So these are my 3 zeros. I have 3 of them, which means I have 3 x-intercepts. These are all my x-intercepts. That's where the graph crosses the x-axis. 3 times. Now, most of these will be factored for you already when they ask you to find the zeros in 4.1. And the ones that are not factored, you should be able to factor them somehow, like factoring by grouping. The window's leaking? Oh my goodness. Is it really? Is it getting on the computer? That's wild. I guess I should probably call somebody. I don't know who I would call. Security or maintenance? I don't even know the phone number for maintenance. Hey, I don't know the phone number for maintenance, but I'm teaching a class in room B209A, and the window is leaking, and it's getting onto one of the computers. Okay. Would you be able to call for me and tell them? Since I'm in the middle of class? Yeah, B209A. Thank you. Okay. All right, moving on. I was gonna wait, but I don't want to get electrocuted or anything. Okay. Okay, so again, like I said, you'll either be able to factor it somehow, factoring by grouping, or it'll already be factored for you. And just remember, you can always use your graphing calculator to check these answers too, because you can graph the function and find the x-intercepts like I've shown you how to do. All right, next thing is we're going to learn about the multiplicity of zeros. So this looks fancy, but it's not that bad. I'm going to explain what it means. This says if x minus c to the k power, where k is greater than or equal to 1, if that's a factor of a polynomial function. So we just seen that in that form up here. I'm highlighting 1 just to show you that's the same thing, right? And we got 2 as the 0 for that, so c is equal to the 0 of that factor. 3 is the k, because that's the exponent on that factor. So if this is a factor of a polynomial function, and x minus c to the k plus 1 is not a factor, and what that means is that there's not more x minus c's somewhere else. Because if there was, for example, let me zoom in and give you an example. if I had x plus 2 cubed and then I had another x plus 2, well, this would actually be equal to what? Exactly. X plus 2 to the 4th. So k would actually be equal to 4. So you just have to be careful of that. Sometimes they'll write them out multiple x plus 2s or x whatever, and you need to combine them all. Just like if it was x cubed times x, that would be x to the 4th power. So that's what that's saying really in green. That's all that means. Okay. So once we do combine them and we do find the highest exponent of that factor k, if k is odd, then we know that the graph crosses at the x-axis at that x-intercept, c, 0. It actually goes through the x-axis. And if k is even, so if the exponent is even, like it is right here, in that example I did with the 4, then c is still a x-intercept, but it is an x-intercept that is tangent to the x-axis. Tangent means that it touches the x-axis, so it will be a point on the x-axis, which is an x-intercept, but then it just bounces back off. So it doesn't actually cross all the way through. So this is just like another property we can use to analyze functions. So, and that k, which is the exponent of the factor, is called the multiplicity of the 0. So going back up to this example we did up here, 2 was the factor, or 2 was the 0 of that factor, right? We got 2 right here. That's what made that factor equal to 0. And the multiplicity of that 0 would be 3, because 3 was the highest exponent on that factor. So let's do an example. And I already graphed this here for you, so we can use it to see. But for this graph, f of x equals x plus 2 squared times x plus 3 times x plus 1. So if I set this equal to 0 to find the zeros, to find the x-intercepts, what would they be? Exactly, -2, -3, and -1. Because I would set all those equal to 0 and then solve, and I'd have to subtract them over. So the zeros are -2, -3, and -1. Okay. The multiplicity, and I'm going to go ahead and write it like this because this is how Pearson will sometimes say it and it can be confusing. But they'll say, what's the multiplicity of the smallest 0? Well, the smallest 0 is -3 because -3 is the smallest number out of that list. That's all it means when they say that. So -3 is the smallest 0. And the multiplicity of that 0 is 1. Because technically there is an exponent of 1 on that factor. Okay. Now let's look at what's happening at that 0. So here's the picture of the graph. -3, the exponent at -3 is right there. And it is crossing through. The graph is crossing through the x-axis at -3. And that makes sense based on what we just learned, because the multiplicity is 1. 1 is odd. So the graph crosses at x equals -3. It crosses through. All right, and then it'll say, what's the multiplicity of the middle 0? I think that's how they word it. When that just means the number in the middle. So the largest one would be -1, so the middle one would be -2. -1 is larger than -3 and -2. What's the multiplicity of the 0, -2? Positive 2.
Is that because of the exponent?
That's because of the exponent.
Okay.
So 2 is even. So when it's even, it bounces off. Or it just touches. And that's exactly what's happening here at this x-intercept at -2. You can see it in the graph. It's just going up and it's touching the x-axis at -2, and then it's going back in the direction it came from. Bounces off, touches and bounces off, however you want to say it. I don't know why bounces helps me remember. Even bounces. Odd crosses. I don't know. Whatever helps you with your remember. Okay, and then finally the multiplicity of the larger 0 which is -1. That's my largest 0 because it's -1 is the largest number out of those 3. That multiplicity would also be 1 because the exponent on that factor, x plus 1, is 1 because it's not there. Or there's not a number there, I should say. So this one also crosses. Which we see in the graph because it crosses at that x-intercept of 1 right there. So this is just another property that you can use to analyze graphs, or use process of elimination to pick the right graph, because you can look at the multiplicity of their 0 and see whether it's crossing or bouncing off like it should. Is there questions about this? Okay. So let's do the example on the back. And within this example, I'm going to talk about something else that you need to know how to do. Okay, so in this example, it wants us to find the zeros. And this is a hard problem, harder than most, but you will see everything in this problem I'm about to do, you will see in your homework. So that's why I've put it all into one problem. All right, find the zeros, state the multiplicity of each, and determine the leading term and the degree of the polynomial, and then we're going to sketch a rough graph given all the information that we learned. So first, let's find the zeros. So to find the zeros, I'm going to set the whole thing equal to 0. And it's already factored, so I can just set each of these factors equal to 0 now. Okay, what would make this first one equal to 0? 0. Because it's just negative 3x or negative 3 times x to the 4th supposed to equal 0. So the only number for x that would make that true is if x is 0. And again, if you wanted to go through the process of solving that, you would have to divide both sides by negative 3. So x to the 4th would be equal to 0. Take the 4th root of both sides, but the 4th root of 0 is 0. So x is equal to 0. What do you think the multiplicity is? 4. Because that was what the exponent on that factor is. It's 4. So 0 is the x-intercept, 4 is the multiplicity. Okay, the next one is x squared minus 25 all cubed is supposed to equal 0. So again, I can cancel that exponent of 3 by taking the cube root of both sides, which is just going to leave me 0 on the other side. So I'm not even going to do that. I just care about what makes the inside equal to 0. Does that make sense? So I'm going to take x squared minus 25, set that equal to 0. And you can solve this in two ways. You can either factor it by using a difference of two squares, or you can use the square root property. So I'm just going to use the square root property. So x squared is equal to 25. Take the square root of both sides, and this leaves me with what? And negative 5 plus or minus 5. So that actually gave me 2 zeros. So this is 2 x-intercepts. The multiplicity of both of these would be 3. Not 2. Yes.
So there's an exponent inside the term or like the parentheses, it does not affect the outside, like the multiplicity at all.
Trying to think of an example. Let me talk through why this is 3 first, and then see if I can answer your question correctly. Okay, let me talk through why this is 3. because first of all, x squared minus 25 factors to x plus 5 times x minus 5, right? And all of that, this is all of this. So it is still cubed if I wanted to rewrite that. Okay? So the exponent of 3 can now be transferred to the first factor and then the second factor. So both of those would still have a multiplicity of 3. So I'm going to say for the purposes of this class, yes, the answer to your question is yes, it doesn't matter because you won't be given something that isn't factored within an exponent. Like, I mean, that, for example, like if you got something like x cubed plus 5 all cubed, this would be a different story. But they're not going to give you something like this. Okay, hopefully that helps. So this is just a side note here of why the multiplicity was 3 for both of those zeros. Okay, now the last two, notice that these are exactly the same, x plus 2 and x plus 2. So from both of these, we just get the 0 of -2, right? And I only need to write it once. And what would the multiplicity be here? 2, because there's 2 of them. And x plus 2 times x plus 2 is equal to x plus 2 squared. So the multiplicity is actually 2. So if they ever repeat a factor, you need to be careful of that. Make sense? All right. So that is the first part. Find the zeros, state the multiplicity of each. So we did that. We had a total of 1, 2, 3, 4 zeros because of the plus or minus 5 on the second part. So 4 zeros. Now, the next part's asking me to find the leading term and the degree. Okay? Now well, I'm about to show you how, but if you didn't know how, you can't determine what the leading term is until you multiply all of that out, right? Because this is factored. So right now, just by looking at it, before I tell you how to do it by looking at it, you can't determine. And I'm not going to ask you to FOIL all of this out to do this. So I'm going to show you how to figure out the leading term, and some of you may already know, by doing this, okay? With what I'm about to show you. So to find the leading term, you're going to first choose all the terms in here that only have an exponent of 1 on their factor. So the first one is -3x to the 4th. And then I'm going to multiply this by the other two x's over there, x times x. And again, I'm getting that from this x, and then I got this term here. Okay? Then the other one is just a little different because it has an exponent of 3, a multiplicity of 3. But if I were to multiply all of that out, if I were to take x squared minus 25 times x squared minus 25 times x squared minus 25, I would end up having to multiply x squared by itself 3 times. Because I'd have to FOIL everything. So really all you need to do is take x squared, multiply it by itself 3 times, which is going to give me what? X to the 6th. You just multiply them. X to the 6th. Does that make sense? And I promise, I mean, if you want to do it by hand and prove it to yourself, you can. But if I cubed that thing and FOILed it twice, I would get a leading term of that as x to the 6th. So I'm just taking the leading term of each group, and now I'm going to multiply them all together. So this would be -3 times x to the 4, 5, 6 plus 6 is 12. This is my leading term. And again, if I multiplied all of that out, took the time to do that, you would get this as your leading term. But I would not expect you to do that. Okay, so the degree is 12. And the degree is even. And the leading coefficient is -3, which is negative. And this tells me, this gives me information about the end behavior, right? Because I just found the leading coefficient, the degree is even, the leading coefficient is negative. So I know that my end behavior, and now we're going to sketch a graph using all this information. Yeah, so the end behavior will look like this. It'll be going down. But I don't know what's happening in between, so I really should do that. But let's just sketch a very, very rough graph here. Okay. So I'm going to start by plotting the zeros. My first x-intercept was 0. My second intercept was -5 and +5. So 1, 2, 3, 4, 5. This would be -5. 1, 2, 3, 4, 5. This would be +5. So that's those 2 zeros in the middle. And then my last x-intercept was -2, 1, 2, which is right here. So that was -5, -2, and 5. And then the middle is, of course, 0. Those are just all the x-intercepts we found, right? Good so far? All I did was plot the points. Okay. Now the end behavior, like we just said, should be both pointing down. So at the very end, last intercepts, I know from this -5, it's going to be going like this. And I know from +5, it's going to be going like this, just based off of my end behavior analysis. Okay, and then let's go back up and talk about the multiplicity. So the multiplicity of 0 was 4. This is even. So it should just bounce off at 0. The plus and the negative 5, I'm going to erase this so I can write this, was the multiplicity was 3, which is odd. So it should cross at those zeros. And then for negative 2, the multiplicity was 2, which is even, so it should bounce again. Okay? So again, this is going to be a very rough sketch of what I'm about to do. It's not perfect, it's just a rough sketch given the information we got. So because at negative 5 it crosses, this will go through and it'll go up some amount and then it'll come back down to negative 2 and it'll bounce off because we just said at negative 2 it bounces. It'll go back up some amount, it'll come back down and go to 0 and bounce off again because that's what we just showed, and then it'll go up and come back down and cross through 5. So it'll do something like this. Now my hoops could be going way further up, I don't know, but I do know that it makes some kind of shape like that. And I will stop there. And I will make another video for 4.2.